In statistical physics, a Langevin equation is a stochastic differential equation describing the time evolution of a subset of the degrees of freedom. These degrees of freedom typically are collective variables changing only slowly in comparison to the other variables of the system. The fast variables are responsible for the stochastic nature of the Langevin equation. Brownian motion as a prototype. The original Langevin equation describes Brownian motion, the apparently random movement of a particle in a fluid due to collisions with the molecules of the fluid. The degree of freedom of interest here is the position x of the particle, m denotes the particle's mass. The force acting on the particle is written as a sum of a viscous force proportional to the particle's velocity, and a noise term I, t, representing the effect of the collisions with the molecules of the fluid. The force I, t, has a Gaussian probability distribution with correlation function, where Kb is Boltzmann's constant and T is the temperature. The I function form of the correlations in time means that the force at a time t is assumed to be completely uncorrelated with it at any other time. This is an approximation. The actual random force has a non-zero correlation time corresponding to the collision time of the molecules. However, the Langevin equation is used to describe the motion of a macroscopic particle at a much longer time scale, and in this limit the I correlation and the Langevin equation become exact. Another prototypical feature of the Langevin equation is the occurrence of the damping coefficient I in the correlation function of the random force, a fact also known as Einstein relation. Mathematical aspects: a strictly I-correlated fluctuating force I, t, isn't a function in the usual mathematical sense, and even the derivative dx dt isn't defined in this limit. The Langevin equation as it stands requires an interpretation in this case, see to calculus. Generic Langevin equation: there is a formal derivation of a generic Langevin equation from classical mechanics. This generic equation plays a central role in the theory of critical dynamics, and other areas of non-equilibrium statistical mechanics. The equation for Brownian motion above is a special case. An essential condition of the derivation is a criterion dividing the degrees of freedom into the categories slow and fast. For example, local thermodynamic equilibrium in a liquid is reached within a few collision times. But it takes much longer for densities of conserved quantities like mass and energy to relax to equilibrium. Densities of conserved quantities, and in particular their long wavelength components, thus are slow variable candidates. Technically this division is realized with the Zwanzig projection operator, the essential tool in the derivation. The derivation is not completely rigorous because it relies on assumptions akin to assumptions required elsewhere in basic statistical mechanics. Let A equals I denote the slow variables. The generic Langevin equation then reads: the fluctuating force I, t, obeys a Gaussian probability distribution with correlation function. This implies the Onsager reciprocity relation J equals Ij, I for the damping coefficients I. The dependence dI, J dAj of I on A is negligible in most cases. The symbol equals ln, Po, denotes the Hamiltonian of the system, where Po, A, is the equilibrium probability distribution of the variables A. Finally, I, Aj is the projection of the Poisson bracket of the slow variables I and Aj onto the space of slow variables. In the Brownian motion case one would have equals P2/2 A equals P or A equals X, P and, Xi, Pj equals II, J. The equation of motion dxm for x is exact, there is no fluctuating force Ix and no damping coefficient Ix, P. Examples: harmonic oscillator in a fluid equals, a non-ideal harmonic oscillator is affected by some form of damping, from which it follows via the fluctuation dissipation theorem that there must be some fluctuations in the system. The diagram at right shows a phase portrait of the time evolution of the momentum, P equals mv, versus position, r of a harmonic oscillator. Deterministic motion would follow along the ellipsoidal trajectories which cannot cross each other without changing energy. The presence of some form of damping, for example a molecular fluid environment, continually adds and removes kinetic energy from the system, causing an initial ensemble of stochastic oscillators to spread out, eventually reaching thermal equilibrium. Equals thermal noise in an electrical resistor equals. There is a close analogy between the paradigmatic Brownian particle discussed above and Johnson noise, the electric voltage generated by thermal fluctuations in every resistor. The diagram at the right shows an electric circuit consisting of a resistance A and a capacitance C. The slow variable is the voltage U between the ends of the resistor. The Hamiltonian reads equals E, 2 kBt, and the Langevin equation becomes. This equation may be used to determine the correlation function, which becomes a white noise when the capacitance C becomes negligibly small. Critical dynamics equals, the dynamics of the order parameter A of a second-order phase transition slows down near the critical point and can be described with the Langevin equation. The simplest case is the universality class model A with a non-conserved scalar order parameter, realized for instance in axial ferromagnets. Other universality classes contain a diffusing order parameters with several components, other critical variables and/or contributions from Poisson brackets. Equivalent techniques, a solution of a Langevin equation for a particular realization of the fluctuating forces of no interest by itself. What is of interest are correlation functions of the slow variables after averaging over the fluctuating force. Such correlation functions also may be determined with other techniques. Fokker-Planck equation equals, a Fokker or Euro-Planck equation is a deterministic equation for the time-dependent probability density P, A, T, of stochastic variables A. The Fokker or Euro-Planck equation corresponding to the generic Langevin equation above may be derived with standard techniques. The equilibrium distribution P, A, T, equals PO, A, equals const, exp, is a stationary solution. Path integral equals, a path integral equivalent to a Langevin equation may be obtained from the corresponding Fokker or Euro-Planck equation or by transforming the Gaussian probability distribution P, I, D of the fluctuating force I to a probability distribution of the slow variables, schematically P, A, da equals P, I, A det. D/da. The functional determinant and associated mathematical subtleties drop out if the Langevin equation is discretized in the natural way, where A, T plus IT, A, T, depends on A, T, but not on A, T plus IT. It turns out to be convenient to introduce auxiliary response variables. The path integral equivalent to the generic Langevin equation then reads, where n is a normalization factor and the path integral formulation doesn't add anything new, but it does allow for the use of tools from quantum field theory. For example, perturbation and renormalization group methods. See also, Langevin dynamics. References. Further reading, W. T. Coffey and U. P. Kolmikov, World Scientific Series in Contemporary Chemical Physics, Vol. 27. Rafe, F. Fundamentals of Statistical and Thermal Physics, McGraw-Hill, New York, 1965. See Section 15.5 Langevin Equation of Friedrich, J. Punk and C. H. Renner. How to quantify deterministic and random influences on the statistics of the foreign exchange market, Phys. Reverend Let 84, 5224-5227, L. C. G. Rogers and E. Williams. Diffusions, Markov Processes, and Martingales, Cambridge Mathematical Library, Cambridge University Press, Cambridge, reprint of 2nd edition, 2000.